Hello everyone. In this video, we're going to be solving an interesting, I want to say exponential, but kind of like a non-standard equation. We have x times e to the power x equals ln 4, and we're going to be solving for x values. To be able to solve this problem, we're going to be using what's called Lambert's W function, which we recently talked about. I've also done a video on the integral of Lambert's W function, which is pretty interesting. Anyways, so how does Lambert's W function work? It basically takes something like x e to the x as an input, and it just outputs the x itself. And obviously, there's different intervals that behave differently. I'm going to talk about those towards the end because I'll show you two graphs that kind of explain what is going on. Okay, great. So this is a really nice property of Lambert's W function. And as you can see, we have x e to the x on the left-hand side. So we can directly apply Lambert's W function. In some problems, in most problems, it's not possible to directly apply it. You kind of have to manipulate the expression and turn it into Lambertable, whatever you want to call that. Anyways, so something like, for example, x plus ln x, right? You kind of have to do e to the power something, and then you can turn it into something like this. Anyways, that's a different story. Let's get to the work. Now, I'm going to Lambert both sides since we have x e to the x, right? Obviously, that makes sense. So w x e to the x equals w ln 4. And this should give us the x value, so you can kind of stop at this point and, okay, we're done, right? No, we're not done yet. Even though that is the answer and that is the exact answer, we kind of want to, get into more details. So what is this? What is w of ln 4, right? What happens if you apply Lambert's W function to ln 4? Can we simplify it? So here's what we're going to do. We're going to write ln 4 as ln 2 squared. And then by using properties of logs, we can go ahead and move this to the front. And this becomes 2 ln 2. This is the most critical part. Whenever you get a number times its ln, we can actually turn it into something nicer. So the question is, how do we Lambertify this? I don't know if that's a word, but even if it isn't, now it is. Anyway, so to be able to Lambertify this, we're going to do the following. Write it to 2 as e to the power ln 2. As you know, x can be written as e to the power ln x, right? As long as x is positive, of course. And if you're dealing with real numbers in this case, complex logarithms are a little different. But we can do this for 2, since 2 is positive. So let's go ahead and replace 2 with e to the ln 2 here. So we get the following. X equals w ln 4, which is equal to 2 ln 2, which is equal to w e to the ln 2 times ln 2, but I'm going to write it as ln 2 times e to the ln 2 because it's the same thing. But this is nicer because notice that it looks like x e to the x, doesn't it? I mean, if it doesn't, then go ahead and call this t, and then you're going to see that it actually looks like t e to the t, which is pretty much the same thing, and you could replace t with x as well. Of course, you shouldn't have an x here. That's a different x, right? Anyways, so let's go ahead and finish this up. What is this equal to? From here, x becomes, because this is equal to t, when you apply Lambert on t e to the t, our answer is going to be t. But what is t? It's ln 2. So the answer is ln 2. X equals ln 2. The million-dollar question, is that the only solution, right? Good question. And let's go ahead and check out the graphs. The graphs are going to give us a good idea how Lambert's W function behaves. So let's go ahead and take a look. First of all, we're going to take a look at the graph of x e to the x. So that should give you an idea. First of all, notice that at x equals -1, we do have a minimum. So our function can be broken into two pieces so that any horizontal line is always going to intersect the graph at a single point. As you know, that is a condition for injectivity, right? And notice that the purple line intersects our graph at a single point anyways, because as x approaches -infinity, our guy here is going to approach 0. Why? Because e to the power negative infinity is basically going to be something like that's going to grow faster than x, so it's going to bring it to 0. Anyways, that's another story. Again, that's about limits, but this tells us that it's not going to cross the x-axis, and we're not going to be able to cross this horizontal line again. So there's a single solution, which is given by x equals ln 2. But in general, we have to be careful because sometimes there's going to be two solutions. Now, imagine our horizontal line went like this, then obviously you would have two solutions. So now let's take a look at another graph which shows us the x e to the x along with y e to the y. So if you switch the roles of x and y, and of course this has to be done on different intervals, then you basically get the inverse function. Notice that these two are inverses and they're symmetrical with respect to y equals x, the diagonal. Of course, that's what inverses do, right? Most of the time. And definitely there's going to be two pieces to this. But since our value is fine, we don't have to worry about it. But that's basically how Lambert's W function behaves on different intervals. All right? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.